Okay, this is a reminder that you have to accomplish the active learning for 40 times. And if you are curious about what is that, then please go to Cyber University to see more information. And now let's look at today's topic. Today's topic is minor number 3, and it is called tree decomposition. So basically, the idea is if you give me a tree, it is a very good structure. Tree is a good structure. And it means that many properties are very nice on a tree. For example, if you have n vertices, then you know that it must have n-1 edges. And this is for whatever the tree that you have, it always have it always has n vertex and n-1 edges. And it is connected. So people call the tree as the minimal connected structure. 这极小的最简单的连通的结构。And it does not contain any cycle. And there are even more nice properties, like between any two paths, between any two vertices, there is a unique path. And it also has a faster algorithm. If you are talking about some problem on a graph, for example, the chromatic number, the dominating number, and the independence number, all these kind of things, and many of them are NP hard, and which means that it is just take a lot of time to calculate it. And so it turns out that in many cases, these algorithms is much easier when the structure is a tree. If you know the graph is a tree, and then the structure, the problem will be faster. The algorithm will be faster. Okay, so the main idea today is we know a tree has a simple and elegant structure, but if we have a general graph, and maybe we can still find the tree-like structure. For example, you see the graph on the right-hand side is definitely not a tree, but it somehow has the instinction that you have that kind of instinction that you want to say, okay, this is somehow like a tree. And so it's pretty similar, right? So let's say our goal is, for any graph, can we describe it as a wider tree? And that brings the idea of tree decomposition. Later on, we are going to describe such a structure in any graph. And any graph can be described as a tree, but how big it is, it depends on the structure. Okay. So let's look at the same example as before. You can use either use the same graph if you wish, or if you could copy, that's also fine. So suppose we have this kind of structure. Let's tell you how the tree decomposition would look like. So basically, you see, you kind of has a feeling that, okay, here is one part, here is one part, here is one part. Okay, so let's call that as T1, T2, and this part is T3. And somehow on the right hand side, you can get a feeling saying, in fact, T1 and T2 are vertices that is connected to T3, right? So the idea is, for each vertex on the right-hand side, it is corresponding to a set on the left-hand side. And you have a relation between these sets, and the relation is recorded as an edge on the right-hand side. And let me try to finish this picture first. It's going to be very ugly very soon. Okay, so this triangle is T4. Okay, let me use a different color. You can say this is T5 and this is T6. And the point is, almost everyone will believe that, okay, this is a structure that looks like a tree. Okay. So it doesn't matter if it's blue color or green color. The whole thing is, I just want to make it clear because there are too many circles on there. So every graph on the left-hand side, the graph on the left-hand side has a structure that pretty much like a tree, and this structure is recorded as a new tree written on the right-hand side. 所以所谓的这种树状的结构呢，它其实要在隔壁自己画出一张树状图。那这张树状图的点呢，它都描述了一些原本的点集都是在左边有一些蓝色的，有一些绿色的这些东西。那每个点呢都代表一个点集。那点集和点集之间呢，有时候会有一些关系，就是它可能是交错啊，然后或者说它自然而然你就觉得这两个点集是碰在一起的。那所以呢，你就可以在右边用一条边来记录一下这些点集。OK。But now let's look at the formal definition, and you will see it is not so easy to get a feeling about the definition at the very beginning. Okay, so our target is any graph. We start with a graph, and we want to talk about the tree decomposition of it. Okay, so the tree decomposition of G is a pair. Okay, and this pair has two things. One is T, the other is a set of vertices. Okay, let me say more about this. So it is a pair, and a pair that has T is just a tree. Okay, so you can imagine that it is something on the right hand side. This one is T. And T has many vertices, T1, T2, T3, and each of the vertex, it corresponds to a subset inside the vertex set of G. So formally, the one that I draw on the left-hand side, it is supposed to be VT1, VT2, and VT3, VT4, VT5, VT6. So you have a tree, and this tree has, say, n vertices, and each of the n vertices correspond to a vertex set on the left-hand side. And such that this structure satisfies the three conditions. Okay, the first one, it says that the vertex set of G should be covered by the union of all these VTIs. Okay, so this means that these things are covering all the vertices. And the second thing is that every edge will be covered. So just like what we have on the left hand top left corner, every edge is inside at least one of the set. Okay, so for example, if you draw an edge that is connecting these two, then that's a problem because this edge is outside of any set. So that's what we want. This is natural because basically you're thinking of a lot of vertex set that covers all the vertices and cover all the edges. 所以这两点应该是比较自然的这些 VTI 呢，它必须要盖住所有的点这是自然的。那再来呢，这些 VTI 呢，每一块呢，它里面每一个点呢，每一条边呢，至少都要在某一个 VTI 里面出现过。你不能说你有一条边是完全跨过任何的 VTI， 一定要至少有一个在里面。Okay, the third one is a bit weird. Okay, so the third one says that if you have 3 vertices on T, I call that T1, T2, and T3. And it just means that, okay, you have some vertex here, and some vertex here, and some vertex here. Okay. So that means they are on the same path. You know, on the tree, every 2 vertices has a unique path. You have a unique path from T1 to T3, and then somehow T2 is one vertex on that. 就是在树状结构里面，任何2点都会有一条path，而且这个 path 是唯一的。那所以现在就是讲说，如果 T2 呢，它刚好就是 T1、T3 中间的其中一个点。Suppose this is the case, then the intersection of VT1 and the VT3, their intersection should be contained in VT2. And this is true whenever T1, T2, T3 are on the same path. And this is referred to as the coherence condition.所以呢，这个东西呢叫做一致性就是说这个必须要这个 tree decomposition 必须要有一些一致的一些感觉。那这也是顺便告诉你说，上面你只是要把点和边把它盖住，这其实应该是蛮简单的。但是呢，点和边盖住其实没有用到太多这个树状的结构嘛，对不对？这棵树你怎么画，感觉都跟第一点跟第二点一点关系都没有。但是第3点呢，就告诉你说，你的左边这个东西要跟你右边的树状结构有一定的连结。那当然，这个连结的方式呢，非常的不直觉至少对你刚碰到的时候，它是非常不直觉的。那当然，很熟悉这些理论的人，他会跟你讲说，没有，这个应该就是这样啊。对，每个老师都会讲这种话。但是就这3个条件。Okay, so let's look at some example to see this. Okay, so let's see. We start with a graph G. Some people call this graph as the fish graph, but it's just a graph they were checking. And now, you see, suppose that you have a graph, then you have to build a tree on the right hand side and use these trees to generate some of the cycles, the vertex sets. So I would say it is probably two vertices, T1 and T2. Just a guess, right? And now let's see if this is VT1, this is VT2, oh, sorry. Okay, cool. Can I start over? Okay, let me leave it like this. Okay, so sorry about that. If you have written something down, then keep it there for a while, and we will think about it later. So now you see that let's review this structure first. Okay, so it's not hard to see that the first condition, the second conditions are satisfied. 就是点和边都有被盖住。Okay. And somehow we need the third condition, and let's try to look at the third condition. Okay. Let's try to see at least one of them as the coherence condition. Okay, and that's what I mean here. Okay. So look at the things above, and then I'm thinking about the one on the left hand side is actually VT2. And the one on the right hand side, this is VT5. Right, and you know VT2, T2 has a unique path to T5. And probably you have a T3 and T4 in between on the path. But now where is the T2, T3 and T4? If you look at here, VT3 looks like this. This is VT3. And if you look at this one, VT4 look like this. It's very ugly, but you can tell what's going on now. Now you can see the intersection of VT2 and VT5 is this part. T2 和 T5 它对应出来的点，这个它只有这个交集。And now you have to see that if this intersection is inside any of VT3 and VT4， 那根据刚刚这个 coherence 的条件呢 ，T2 和 T5 的交集呢，它必须要被包在中间的任何点上。那你从 T2、T3、T4、T5， 你每一个集合呢，你仔细看它实际上这个交集呢，被 VT2、VT3、VT4、VT5 都包住了。OK， 所以在这个情况下呢，它是 OK 的。So this is somehow telling that if you want to switch from VT2 to VT5, there are something that you never changed. Then all the things in between, you have to condense this part. It's a kind of continuous change. 意思就是说 T2 到 T5 呢，你要从这个集合慢慢的转换到 T5 这样的话呢，那就表示说你这一区都没动嘛。那你既然这一区到这一区，你要从 T2 到 T5 这一区都没动的话，那你中间演变的所有过程中，应该都要包住它。这样看起来比较合理一点。So that's called a tree decomposition. Sorry. And now, each of the VTI is called a tree bag. Okay, just a name. It's a name.